This lesson is about normal distributions. So many random variables are actually normally distributed, which means a few things. It means they have a bell-shaped curve. So their probability distribution histogram looks like this curve here. They're symmetrical about the mean. So I've got my mean here, and there's equal number of scores on either side. And they share certain properties about the percentages of scores which lie within a number of standard deviations from the mean. So you see this red arrow, it means one standard deviation either side should have about 68%, about 2/3 of the scores. Okay, see these yellow arrows, so 2 standard deviations from the mean should be about 95% of the scores, and the pink 99% of the scores should be within 3 standard deviations of the mean. Okay, some other things, the area under the curve is 1. Okay, so if I calculate the area of this whole section is 1, and the area between any two values is the probability of it being selected. Okay, so that's just your normal probability distribution histogram property, but we'll look at that. Okay, so a normal distribution does follow this equation. Okay, we don't need to memorize this equation, but know that it exists. Okay, so essentially what this is saying is, for example, for intelligence quotients, we have a mean of 100 and a standard deviation of 15 in the population, and we could substitute these two values into where it has our standard deviation and our mean and find that function. And then if I wanted to find, say, what's the probability of someone having an IQ between 85 and 115? It means I'm trying to find this shaded area. Okay, which means that I'd find the integral between 85 and 115 of this big function. Yeah, that doesn't sound very fun at all, does it? Take you ages to do, probably make lots of errors. Okay, even when we substitute numbers for mu and sigma. Okay, so we're not going to do that. Okay, we generally won't be doing that in this course. Okay, just thinking, one thing to note before we move on. So we do have two different expressions for the mean, but in here, the standard deviation will always be shown as sigma. Okay, don't need to worry about difference between x bar and mu. It's just population and standard means, but for us they'll always be the same. Okay, so here's two other examples of things that are normally distributed. If I look at the stock market and how it changes each day, for a particular share, for Yahoo, even though Yahoo's pretty much dying at the moment, this is historically what's happened over the last year. So on some days, Yahoo's share price has gone up almost 9%. On some days, it's gone down 6.5%. But generally, it's going plus or minus 1% or 2%. Okay, so the daily percentage change has a mean of 0.037 and a standard deviation of 1.86. Okay, standard deviation, measure of how spread out it is. This final one is the one we'll use for most of our examples. It could be the height of our maths class, with a mean height of 177 centimeters and the standard deviation of heights of 8 centimeters. Okay, so these two scores, so 169 is 1 standard deviation below, 185 is 1 standard deviation above. I know that this area is going to be 68%. Okay, once I do the integral, I'll get 68%. Okay, so let's have a look at doing some calculations. So just thinking about these three different standard they're not standard normal distributions, they're just normal distributions. Looking at these three normal distributions, we see that if I want to calculate probabilities for these three, I'd have to substitute mean and standard deviation into this formula, and it'd be different every time. Okay, so over the page, what we have is this idea of standardization. Okay, so while it's possible to integrate the formula for every type of distribution, it's more useful that we'll just find the areas under the curve for one type of distribution and then use that for every other type. So I've got a normal distribution here where my mean is 1010 and looks like my standard deviation is 20. These are x values. Okay, it's useful for us to convert those x values to z values where the mean is 0 and the standard deviation is 1. So the way we do this standardization is by using this formula for our z values, which is going to tell us how many standard deviations the score is above or below the mean. So if I take a score of 1050, for example, okay, an x value of 1050, that would correspond to a z value. So subtract the mean divided by the standard deviation. That would correspond to a z value of 2, which means it's 2 standard deviations above the mean. And then we can use some of these graphs that we have around, or some of these tables that show us all these areas that we might be interested in. Okay, we might be interested in probability of x being greater than 1050. Okay, and I could look on this table once I've converted it to a z value and find what this area is. Okay, so that's the whole idea behind standardization. So let's have a go at a problem. Okay, I got an IQ problem. Find the probability a randomly selected person has an IQ between 100 and 140. So I'm trying to find between 100 and 140. So 140 is out here somewhere. I'm trying to find this shaded area. Since I won't always have that diagram, I'll draw my own little diagram. Remember, mean is 100, standard deviation is 15. I want between 100 and 140. Okay, this shaded area. I'm trying to find the probability that x is between 100 and 140. So this is a normal distribution. Okay, so what I want to do is convert this to a standard normal distribution. Okay, which has a mean of 0 and a standard deviation of 1. And I want to find that corresponding area. So for 100 and 140, I'm going to perform this standardization. So when x equals 100, what does z equal? Okay, so I'll write my z formula. So x minus mean divided by standard deviation. I get a z value of 0, so it's from 0, and then do the same thing for 140. And I get 2.66. So these two areas in the normal distribution and standard normal distribution will be equivalent. These are z values. So I'm looking for the probability of z being between 0 and 2.66. So back in the olden days, I'd have to use these tables to look it up. But now that we're in 2016, I can use my graphics calculator. So if I want to find this probability, I go into my stat mode. I've got a distribution, F5, and it's a normal distribution. And I want to find an area, so I'm looking at F2. I'm going between 0 and 2.66. Lower. So lower is 0, upper is 2.66. And this is set up for a standard normal distribution with a mean of 0, standard deviation of 1. So I can execute this, and I'll get my probability of 0.496. Okay, which I can get off my table if I'm really keen. Okay, so that's how we'll calculate probabilities with the standard normal distribution. Okay, but it's important that you understand standard normal distributions for some of the problem solving that we'll be doing in the future. However, your graphics calculators are that good that we can just use the normal distribution. Okay, so we could say, well, my lower is 100, my upper is 140, my standard deviation is 15, and my mean is 100. Okay, and I'll get that same 0.496. Okay, so told you a little bit of a lie because this thing in green is all that's required for the solution. Okay, but it's a good time for you to understand standard normal distributions and see how it relates to the normal distribution. So what we'll do is roll through a few examples so you get comfortable with finding these probabilities. Look at a few abstract examples first. If X is normally distributed, X is normally distributed with a mean of 30 and a standard deviation of 5, find the probability that X is greater than 40. Okay, I'm trying to find the probability that X is greater than 40. So I'll go into the same mode. So in stat mode, I've got a distribution, normal distribution, I want to find an area. So my lower value is 40. I don't have an upper value, so I'll just put in some big number. Standard deviation of 5, mean of 30. Good to go. 0.023. Okay, example 2, we've got an abstract standard normal distribution, which implies that my mean is 0 and my standard deviation is 1. Okay, you need to have that knowledge. Again, draw my diagram. Mean of 0, standard deviation of 1. I want to go between -1 and 1. I want to find this shaded area. Again, off my graphics calculator. So I'm between -1 and 1. Standard deviation of 1, mean of 0, 0.683. Okay, so those are abstract examples where we're just talking about these curves. Now we can look at a life-related example relating to the heights of students in our class. So we know we've got a mean of 177 and a standard deviation of 8. Find a probability that a student is between 158 and 183. Okay, and can be a flight attendant for Qantas because that's their limits. So here's my X values. Mean of 177, standard deviation of 8. I want to go between 158 and 183. I'll find this shaded area. So I'm finding the probability of it being 158 to 183, put x in the middle, and less than or equals to, it doesn't matter. And we're off to our calculator again. Between 158 and 183 with a standard deviation of 8 and a mean of 177. Okay, so 76.5% or 0.765. That percentage of the class can be a flight attendant for Qantas. Okay, part B, probability that a student's taller than 130. Okay, so I've got this same distribution. I want it to be taller than 130, so I want this whole shaded area. I think it's going to be pretty much everyone, but I'll do the calculation anyway. So I'll go into my calculator. In this instance, I want from 130 to infinity, so a big number. Execute on that, 0.99999, yep, essentially everyone. Why isn't it 100%? Well, it's just saying that there may be a case where there's some extreme outlier who's shorter than 130. Okay, and the last one, if the student's shorter than 240 centimeters and can walk through a standard Australian doorway without ducking. Okay, so let's just see what's the probability of a student being below 204 centimeters. So I'm after the probability that x is less than 204. Again, to my graphics calculator, I want from negative infinity, so just negative some big negative number up to 204. Okay, same standard deviation, same mean, you get 0.9996. Okay, so it's pretty unlikely that given this mean and standard deviation that we have someone who actually has to duck to go into a standard walkway, which is good because we want people to walk through without too many dramas. Okay, from here, have a practice at exercise 10A. Okay, good luck.